Welcome back to Mr. Guard's Maths class. This is the first topic in the larger topic known as probability and statistics. We will be looking today at interpreting graphs and tables. We can gather data from surveys or so many different ways of collecting data. How we actually use that data is what's important in maths and especially in science. We have in this unit two overarching types of data. There's numerical data in red and categorical data in blue. We're going to start by looking at numerical data. Now the name might suggest numerical means numbers. So it's data that's collected using numbers. You can see that I've branched this slide out into discrete and continuous. So there are two types of numerical data, discrete and continuous. Discrete data are individual units. So a few examples might be shoe size, because shoe size, generally speaking, comes in size 7, 8, 9, or maybe 7.5, 8.5. You never really find a shoe size that is, say, 8 4/5, or my shoe size is 10.2. We have set sizes, so they have discrete values. Another example might be actual age or what year group you're in. So you might be in year 8. You don't have a year 7.3 or a year 12.5. You have year 7, year 8, year 9, and so on. So discrete data are numbers. So you might be 12, 13, 14. Whereas continuous data is where you can break down those numbers. An example that we're going to look at is height. So you can be, if we're looking at centimeters, you can be 170 centimeters. But if we wanted to get really specific, we could. We could say you are 170.38 centimeters. So that's what we call continuous data. A really common one for continuous data as well is time. So if we were looking at running the 100-meter running race, we don't just say 11 seconds, 12 seconds, 13 seconds. We can actually say 12.11, 12.12, 12.13. And if you really wanted to get specific, as they do in sort of motor racing, is you could get down to 12.135, 12.136, etc. In other words, you can get extremely specific and the numbers are ever changing. So we'll start by looking at the two red graphs that I have here. The left-hand side is for discrete data and the right-hand side is for continuous data. And for the first one, discrete, which are individual numbers, so that was like the shoe size or the year group that you were in, I've got a graph that's got siblings, meaning how many brothers or sisters does a person have. So we haven't done a survey, obviously. It might be something that you do in a classroom setting, but we're going to just make up some numbers here. So we could survey a class and find that having 0 siblings, there were 2 people in the class that had 0 siblings. And then if we continued on the survey, we might find that 3 people had 1 sibling. Let's say 5 people had 2 siblings. Then you might find that there are just 2 with 3 siblings and 1 person with 4 siblings. So you might get a graph that looks something like that. Now, it's important to note that we can actually have a bar graph, which is this type of graph, because you can't get 1.5 siblings, or there is not 2.37 brothers. So each number on the x-axis has a finite number. You've got 0 or 1 or 2 or 3, but you don't have a number in between. So we use a bar graph or a column graph. We don't draw a line graph, as you'll see in a minute. Something worth noting is we do sometimes leave a little gap here, especially if the number's not starting at 0. In this case, it did start at 0, so we wouldn't have to leave that there. You'll see on my next graph, I've done a little squiggly lightning bolt looking line here. That indicates that jumping from 0 to 140 sort of is not to scale. So it's sort of saying that there are a whole heap of, in this case, heights of people that we're not interested in. So if we were looking at a class group of year 8s, we're not probably expecting too many people, let's say less than a meter in height. Obviously that, could be an exception, but in this case we're not going to include anyone that is under 140 centimeters. So again, height can be or is continuous data, because while you might be 170 centimeters and the guy next to you or the girl next to you might be 171 centimeters, you can have a height that fits in between 170 and 171. In fact, you could have 1,000 different heights in just that 1 centimeter range, depending on how accurate you want to get with your measuring. So when we do one of these graphs, commonly the number on the left or the y-axis requires a large number of people to be involved. So you might find, for example, you have a lot of people around that 160, and you find a graph that looks something like that. That is similar to what's called a bell curve. It's commonly found in lots of data sets where there's sort of an average height. So in this case, it looks like 160 centimeters is about the average height for a year 8 person. And then you're going to get less and less as the height increases. So there are not going to be too many 2-meter tall year 8 students, but there will be the very, very rare person that's 2 meters in year 8. Likewise, as you go down the other end, you're not going to get many 1 meter tall year 8s, but the bulk of the people are going to be in this 160 centimeter range. Now, it's just worth noting that I've kind of made these numbers up, so don't take them for gospel. But ultimately, this becomes a line graph, because you can have someone, if you wanted to work out how many people were 151.2 centimeters, might fit somewhere up here, and you could work out there is this many people, whatever that number equated to. You couldn't, on the other hand, with the discrete data, see how many people had 2.5 brothers, because that just wouldn't work. Now we're going to have a quick look at categorical data. Categorical data is, as the name suggests, to do with categories. Now, in this case, we can start moving away from thinking about numbers, and we commonly look at animals or colours or things along those lines. And in this case, we're talking about houses at a school, so that's how you break up students. So lots of schools might have people that are in the blue house or the blue group, the red group, the green group, and the yellow group. You could run a survey of your class and find out how many people fit into those categories. Now, this is discrete data because you're not going to have someone that's, in this case, halfway between blue and red. So we might find that we have something that looks like this. Probably should have lined those up a little bit better, but that one, for instance, is 3, 4, 2, and that can be 5. So we could say in this class there looks to be 14 people. 2 people are in the blue house, 4 people in the red house, 3 people in the green house, and 5 in the yellow house. Now it's important that we make sure that this is not drawn like a line graph. It would look a little bit silly if it went something like this. If we had done that, that would indicate that there's a value at that point, which is impossible. You can't have someone that is partly in the red house and partly in the green house. You are in one of the discrete categories. Other examples that can sometimes be used in surveys is maybe picking your favourite football team. And so there'll be this many people that picked, let's say, the Geelong Cats in the AFL, or 7 people that picked Manchester United in the English Premier League, and so on. But you can't have 3.5 people supporting a team. So now we've seen bar graphs or column graphs, which are the ones with the rectangles, and we have seen a line graph, which is the one that we did on height. And one of the final ones that we're going to look at is a pie graph. A pie graph is, as the name suggests, a circle that looks like a pie, and it's cut into segments. Now my thinking is that I'm going to do this based on the data from above in the houses at school. Now I haven't made this easy for myself by making out 14 different people. Each person is going to represent 1/14 of this circle. So I'm going to just do this one by hand and we'll see how we go. So if we were going to look firstly at the yellow section, if we start there, we've got 5/14, which is going to look something like about that amount. If we had a look at, let's go for the greenhouse. The greenhouse has 3, so I think it's going to look something like that. The red house has 4. I don't think I've done this too well. I don't think I have, no. Anyhow, you get the idea. That's 4. And then the blue house is this section in here. Represents 2. That is a pie graph. It is worth, we sometimes see these because they're a really quick visual representation of the distribution. A bit like the column graph, you can quickly see just by looking at it, especially if it's actually drawn accurately, unlike mine, that the yellow house has the most people, the green house and the red house have somewhere in the middle, and the blue house has the least number of people. What's often easiest is if you divide that by the number of people that have been surveyed, in this case 14, and then you allocate a segment to each person. It's been a long video, but it's an important introductory one for this topic. Thank you for listening, and I'll see you in the next one.